Okay. Listen. Good. Withdraw.
We just made a transfer of some liquid helium out of a storage tank into our own experimental equipment. Helium is a remarkable substance. It has two different and easily distinguishable liquid phases, a warmer and a colder one. The warmer phase is called liquid helium-1, and the colder phase, liquid helium-2. The two phases are separated by a transition temperature, known as the lambda point. When liquid helium is cooled down through the lambda point, a transition from helium-1 to helium-2 is clearly visible. We will show it to you later in this film. The two liquids behave nothing like any other known liquids, although it could be said that helium-1, the warmer phase, approximates the behavior of common liquids. But it is helium-2, the colder phase, which is truly different. Because of this, it is called the superfluid. The temperatures involved when working with liquid helium are quite low. Helium boils at 4.2 degrees Kelvin under conditions of atmospheric pressure, and the lambda point lies at roughly 2.2 degrees. Note that this corresponds to minus 269 and minus 271 degrees centigrade. The properties of liquid helium that I've just been telling you about are characteristic of the heavy isotope of helium, helium-4. The element occurs in the form of two stable isotopes. The second and lighter one, helium-3, is very rare. Its abundance is only about 1 part out of 10 million. Pure liquid helium-3 is the subject of intensive study at the present time, but so far no second superfluid liquid phase has been found to exist for helium-3. The low temperatures at which we'll be working call for well-insulated containers. The dewar meets our requirement. The word dewar is the scientific name given to a double-walled vessel with the space between the walls evacuated. When these dewars are made of glass, the surface of this inner space is usually silvered to cut down heat transfer by radiation. However, our dewars will have to be transparent so that we can look at what's going on inside. Now, liquid helium is commonly stored in double dewars. The design is quite simple. Just put one inside the other, like this. In the inner dewar, we put the liquid helium, and in the space between the inner and outer dewar, we maintain a supply of liquid air. Here is a double dewar, exactly like the one we will be using in our demonstration experiments. The inner dewar is filled with liquid helium. The outer dewar contains liquid air. The normal boiling temperature of liquid air is about 80 degrees Kelvin, 75 or more degrees hotter than the liquid helium. The purpose of the liquid air is twofold. First, we put the liquid air in the outer dewar well ahead of putting liquid helium in the inner dewar. In this way, the inner dewar is pre-cooled. Secondly, we maintain a supply of liquid air in the outer dewar because it provides an additional mantle of insulation now that the liquid helium is in the inner dewar. The boiling of the liquid air attests to the fact that it is absorbing some of the heat which entered the double dewar. Even with the boiling of the liquid air, the liquid helium is clearly visible. Later, we will use liquid air cooled below its boiling temperature to reduce or eliminate the air bubbles for better visibility. Now the liquid air is cooled down and we have eliminated boiling. The smaller bubbles of the boiling liquid helium are clearly visible. The cover over the inner dewar has a port, at present open. The liquid helium is at atmospheric pressure, so its temperature is 4.2 degrees Kelvin. In other words, what we have in here now is liquid helium-1, the warmer of the two phases. Before we cool it down to take a look at the superfluid phase, I want to dwell briefly on the properties of helium-1. I've told you before that even helium-1 is different from the normal liquids. The distance between neighboring atoms in this liquid is quite large. The atoms are not as closely packed as in the classical liquids. The reason for this is quantum mechanical. The zero-point energy is relatively more important here than in any other liquid. As a consequence, liquid helium has a very low mass density, only about 13% the density of water, and a very low optical density. The index of refraction is quite close to 1. This makes its surface hard to see with the naked eye under ordinary lighting conditions. You are no doubt familiar with the fact that the helium atom has closed shell atomic structure. This explains why helium is a chemically inert element. It also accounts for the fact that the force of attraction between neighboring helium atoms, the so-called van der Waals force, is small. It takes little energy to pull two helium atoms apart, as for example in evaporation. This gives liquid helium a very small latent heat of vaporization. Only 5 calories are needed to evaporate 1 gram. Compare this with water, where evaporation requires between 500 and 600 calories per gram. The low van der Waals force, combined with a large zero-point energy, also account for the fact that liquid helium does not freeze, cannot be solidified at ordinary pressures, no matter how far we cool it. However, liquid helium has been solidified at high pressure. The liquid helium in the dewar is at 4.2 degrees. We now want to cool it down to the lambda point and show you the transition to the superfluid phase. Our method will be cooling by evaporation using a vacuum pump. Now, the lambda point lies at 2.2 degrees, only 2 degrees colder than the present temperature of the liquid. What's more, not very much heat has to be removed from the liquid helium now in the dewar to bring it to the lambda point. It amounts to only about 250 calories. Nevertheless, don't get the idea that this cooling process is easy. On the contrary, it's quite difficult. More than 1/3 of the liquid helium now in the dewar has to be pumped away in vapor form before we can get what remains behind to the lambda point. That requires an awful lot of pumping and explains why we use this large and powerful vacuum pump over here. Even with this pump, the cooling process takes a considerable amount of time. Why it is so difficult to cool liquid helium to the lambda point. I have already mentioned that liquid helium has a remarkably small heat of vaporization, only 5 calories per gram. At the same time, liquid helium at 4.2 degrees has a high specific heat, almost 1 calorie per gram. Therefore, 1 gram of the vapor pumped away carries with it an amount of heat which can cool only 5 or 6 grams of liquid helium by 1 degree. That's not very much cooling. It is less by a factor of almost 100 than when we cool water by evaporation. The situation gets even worse as cooling progresses below 4.2 degrees, because the specific heat of liquid helium rises astonishingly as we approach 2.17 degrees, the lambda point. The heat of vaporization, on the other hand, remains roughly the same. So, a given amount of vapor carried off produces less and less cooling as we approach 2.17 degrees. Our thermometer here is a low pressure gauge connected to the space above the liquid helium. The needle registers the pressure there. It is the saturated vapor pressure of liquid helium. The gauge is calibrated to the corresponding temperature. We call it a vapor pressure thermometer. As we approach 2.17 degrees, boiling becomes increasingly violent. Suddenly it stops. This was the transition. The liquid you now see is helium-2. Even though evaporation does continue, there is no boiling. Normal liquids, such as the water in this beaker, boil because of their relatively low heat conductivity. Before heat, added at one point, can be carried away to a cooler place in the liquid, bubbles of the vapor form. Helium-1 behaves like a normal liquid in this respect. The absence of boiling in helium-2 reveals that this phase acts as if it had a large heat conductivity. As a matter of fact, as the liquid helium passed through the lambda point transition you just saw, its heat conductivity increased by the fantastic factor of 1 million. The heat conductivity of helium-2 is many times greater than in the metals silver and copper, which are among the best solid heat conductors. And yet, here we deal with a liquid. For this alone, helium-2 deserves the name of superfluid. Actually, the way in which helium-2 transports such large quantities of heat so rapidly is totally different from the classical concepts for heat conduction. I'll come back to the subject later in connection with an experiment demonstrating the phenomenon of second sound in helium-2. Remember that this great change in heat conductivity occurs at a fixed transition temperature, the lambda point. We do indeed deal with a change in phase, only here it is a change from one liquid to another liquid. As we've told you before, the specific heat of liquid helium is very large at the lambda point. In fact, it behaves abnormally even below the lambda point and falls again very rapidly with the temperature. This discontinuity in specific heat is another reflection of the fact that we are dealing with a change in the phase of the substance. By the way, the curve resembles the Greek letter lambda. The transition temperature got its name from the shape of this curve. We are in for more surprises. The next one has to do with the viscosity of liquid helium. When a normal liquid flows through a tube, it will resist the flow. In this experiment, we shall cause some glycerin to flow through a tube under its own weight. The top layer is colored glycerin. The liquid layer closest to the tube wall adheres to it. The layer next in from the one touching the wall flows by it and is retarded as it flows due to the interatomic, the van der Waals force of attraction. The second layer, in turn, drags on the third, and so on inward from the wall, producing fluid friction, or viscosity. The narrower the tube, the slower the liquid's rate of flow through it under a given head of pressure. Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity. Many capillary channels run through this ceramic disc. Their diameter is quite small, about 1 micron, which is 1/10,000th of a centimeter. There is liquid helium in the beaker. It is at 4.2 degrees Kelvin. Helium-1, the normal phase. The capillaries in the disc are fine enough to prevent the liquid now in the beaker from flowing through under its own weight. Clearly, helium-1 is viscous. To be sure, its viscosity is very small. That's why we had to choose extremely fine capillaries to demonstrate it. Here you see the lambda point transition. The helium-2 all pours out. The rate of pouring would not be noticeably slower if the porosity were made yet finer. We call this kind of flow a superflow. The temperature is now at 1.6 degrees. The superflow is even faster. The viscosity of helium-2 in this experiment is so small that it has not been possible to find a value for it. It is less than the experimental uncertainty incurred in attempts to measure it. We now believe that helium-2, the superfluid, has zero viscosity, although we should be more precise here. We believe its viscosity is zero when observing capillary flow. Bear this statement in mind, for we will come up with a contradiction to it in the next experiment, where we will look for viscosity by a different method. There is a copper cylinder in the liquid helium, so mounted that we can turn it about a vertical axis. In order to turn it smoothly and with as little vibration as possible, we make the cylinder into the armature of a simple induction motor energized from outside the doer. The 4 horizontal coils you see provide the torque which turns the cylinder. The liquid helium is electrically non-conducting. The coils exert no torque on it directly. Yet, as we turn on our motor, the liquid layer bounding the cylinder is dragged along by it. The boundary layer, in turn, drags on the next layer, and so on outward. Finally, a circulation shows up in the helium due to its own viscosity, and the wooden paddle wheel is turned along. What we have just seen occurred in helium-1, the normal phase, at 4.2 degrees Kelvin. That is to say, this demonstration is consistent with our results for helium-1 by capillary flow. Helium-1 is viscous. Here you see the liquid cooled down and passing into the superfluid phase, helium-2. Let's turn on the motor. The paddle wheel starts again. What does this mean? First of all, let me emphasize that, like helium-1, helium-2 is also non-conducting in the electrical sense. In other words, the circulation in the experiment can only have been caused through viscous drag. So we conclude from the rotating cylinder observations that helium-2 is viscous, and from the method of capillary flow that it has zero viscosity. Our experimentation has come up with a paradox. No normal classical liquid is known to behave so inconsistently in capillary flow on the one hand and in bulk flow on the other. This state of affairs forces us to think of helium-2, the superfluid, not as a single, but as a dual liquid. It appears as if helium-2 had 2 separate and yet interpenetrating component liquids. We shall call one component normal. It is this component which we hold responsible for the appearance of viscosity below the lambda point in the rotating cylinder experiment. The normal component, as the name suggests, behaves like a normal liquid and therefore has viscosity. It is the one which the cylinder drags along as it turns. But the normal component cannot flow through the narrow channels of the ceramic disc because of its viscosity. The second component has zero viscosity, and it's called the superfluid component. We think that it does not participate at all in the rotating cylinder experiment below the lambda point. It stays at rest. On the other hand, it can flow through channels of 1 micron diameter with the greatest of ease, encountering no resistance whatever, because it has no viscosity. As we'll see later, this flow is not impeded even when the capillary diameters are made far smaller than 1 micron. This thought construction is called the two-fluid model for liquid helium-2. Whether it is correct or not depends on further tests comparing the theory based on this model with experimental results. We now go on to another phenomenon, the fountain effect. What you see here is a tube which narrows down and then opens into a bulb. A small piece of cotton is stuffed into the constriction between the tube and the bulb. And the bulb has been tightly packed with one of the finest powders available, jeweler's rouge. A second wad of cotton keeps the powder in the bulb. This powder presents extremely fine capillary channels. Their average diameter is a small fraction of 1 micron. This device has been placed in the dewar. The liquid helium is below the lambda point. We submerge the bulb, and then we'll send a beam of light from this lamp to a point near the top. You will see the light beam when the lamp is turned on. It focuses some heat in the form of infrared radiation on the point in question. The temperature will rise above the temperature of the rest of the apparatus. Let us turn it on. Liquid helium flows through the hole in the bottom of the bulb, through the fine powder, and rises above the level of liquid helium outside. The height to which it will go depends on the temperature increase produced by the lamp focused on the bulb. We can very well ask, where does the mechanical energy come from that does the work necessary to pump the liquid above the ambient level? Before we attempt to discuss this question, there are two other facts that should be noted. The first is by now obvious. The upward flow through the bulb must clearly be a superflow. Only the superfluid component of helium-2 could get through. The second fact is more significant. Let me explain it this way. The superfluid flows spontaneously from A to B, from a cooler to a warmer place. Point A is in the cold liquid, but B is being heated with infrared rays. The second law of thermodynamics positively says that heat cannot of itself flow from a point of lower to a point of higher temperature. What does this mean to us here, knowing as we do that the superfluid is flowing from a colder to a warmer spot? Simply this: it carries no heat, no thermal energy. Any internal energy it may still possess is no longer thermally available. To say it precisely, it has zero entropy. We have discovered another remarkable property of helium-2. Its superfluid component not only is friction-free, it also contains no heat. The heat energy contained in helium-2 as a whole resides, all of it, in the normal component. We may of course add heat to the superfluid component, as we are doing when it passes the spot heated by the lamp. But in doing so, we are converting it into the normal component. Let me return briefly to a question posed earlier. Mechanical work is done in pumping the liquid above equilibrium level. Where does it come from? I cannot answer this question here in full. Let it suffice to tell you that we are dealing here with a heat engine. The mechanical energy comes from the heat added at the light spot. An amusing demonstration of the same phenomenon again uses a bulb packed with rouge, but this one opens into a capillary. Light is beamed on a spot just below the capillary, and it produces a helium fountain. The phenomenon in this and the previous experiment has become known as the thermomechanical or the fountain effect. Below the lambda point, the superfluid component of liquid helium creeps up along the walls of its container in an extremely thin film. It is known as the Rollin film. This creeping film is a variety of superflow. It is difficult to make the film itself directly visible to you. To show it indirectly, we've put some liquid helium into a glass vessel. It is below the lambda point. There is no porous bottom in this vessel. The film rises along the inside wall and comes down along the outside, collecting in drops at the bottom. The thickness of this creeping film is only a small fraction of 1 micron and of the order of 200 to 300 angstroms. Its speed, while small just below the lambda point, may reach a value as high as 35 centimeters per second at lower temperatures. Our next experiment deals with the phenomenon of second sound. We are all familiar with wave motion in elastic materials, be they solids, liquids, or gases. Elastic energy of deformation carried away from a source in the form of waves with a characteristic speed, the speed of sound. Liquid helium is an elastic substance, both above and below the lambda point. Both helium-1 and 2 support sound waves. Now, helium-2, the superfluid phase, also conducts heat in the form of waves. This remarkable property is shared by no other substance. For better or for worse, it has been called second sound. Normal heat conduction is a diffusion process. The rate of flow of heat is proportional to the temperature differences. But in helium-2, it is a wave process. Heat flows through helium-2 with a characteristic speed, the speed of second sound. We shall send small heat pulses into helium-2 from a heater. They will spread away from the heater uniformly, carrying the heat energy with them. The speed of second sound is small, just below the lambda point. In the neighborhood of 1.6 degrees Kelvin, it reaches a value of roughly 20 meters per second, and it is in this range that we will run our demonstration. The experimental procedure is as follows. There are 2 discs in the liquid helium. They are carbon resistors, with the carbon applied in thin layers on one side of each disc. In this way, good thermal contact is established between the resistor and the liquid helium. The bottom resistor will be used as a heater. Electric current will be sent through it in pulses from this pulse generator by means of the cable you see here. The output of the generator is also connected via a second cable to a dual trace oscilloscope, where it will be recorded on the bottom trace. In other words, it will record the heat pulse as it enters the liquid helium. The pulses have been turned on. They themselves trigger the horizontal sweep of the trace, which records time elapsed. It is calibrated at 1 millisecond per unit on the scale. The pulses are 1 millisecond long. The pulses leave the heater at the bottom in the form of second sound and move up to where they strike the carbon resistor at the top. Being heat pulses, they briefly raise its temperature. The carbon resistor is quite sensitive to changes in temperature. So, the heat pulse of second sound creates a pulse-like change in the resistance of the disc up here. It isn't hard to convert this resistance pulse into a voltage pulse. What we will do is to maintain a small DC current in the top resistor. It is supplied from a battery in this metal box. The box shields the circuit in order to reduce electronic noise. The voltage pulse is small. In this second box, we have an amplifier. The amplifier output is fed into the oscilloscope, where it will appear on the upper trace. The horizontal time scale on this trace is exactly the same as for the bottom trace. However, the upper trace records voltage changes as they occur in the top resistor, the detector of second sound. The temperature of the liquid is about 1.65 degrees Kelvin. The battery has been turned on. And now the amplifier. Among noise and other distortions in the upper trace, a clear-cut voltage pulse appears, about 4.5 units to the right, 4.5 milliseconds later than the pulse entering the heater. This pulse in the upper trace is also about 1 millisecond long. It is the second sound as it arrives at the upper resistor. The upper trace also shows a strong voltage pulse at the left, simultaneous with the heater pulse. That's due to pickup by electromagnetic wave, with the heater acting as transmitter and the detector as receiver. We are moving the detector towards the heater. The pulse moves with it to the left. Notice the echoes of second sound which appear on the upper trace while the detector is near the heater. They are caused by multiple reflection between the two resistors. A total of 3 echoes is clearly visible. Moving the detector away from the heater increases the delay. Here we have the resistors at their original distance again. They are 9 centimeters apart. The wave of second sound covers 9 centimeters in 4.5 milliseconds. The speed of second sound is 2 centimeters per millisecond, or 2,000 centimeters per second, or 20 meters per second. Let me return to the discussion of the two-fluid model for liquid helium-2. We find that it gives us an adequate qualitative description for the behavior of helium-2. The superfluid component is frictionless and free of entropy. It is thought to be the part of helium-2 which leaks through the finest pores, which rises up toward the source of heat in the fountain effect, and which creeps up along the walls of the container. The normal component, on the other hand, is viscous and possesses some available heat energy. The normal component is thought to be that part of helium-2 which is dragged along by the rotating cylinder and which remains behind in the beaker with a porous bottom unless it is first converted to the superfluid component. Now, a model alone is not a theory. It turns out that quantum mechanics has had to be brought to bear on the problem of producing an accurate check between theory and experiment. As is usual, when we attempt to explain a quantum mechanical system by a classical model, this model gets lost, becomes washed out, so to speak. It's there, but then again it isn't. The model is false, but many of its elements survive. That's what has happened to the two-fluid model for liquid helium-2. Helium-2 must now be considered as a quantum mechanical system. It is still true that helium-2 is capable of 2 different types of motion, but we cannot anymore claim that these 2 motions occur on different parts of the liquid or on different groups of helium atoms. Rather, we should look at it all as one liquid system capable of 2 different types of motions simultaneously. The superfluid motion, a perfect fluid flow, reversible in the thermodynamic sense, and the normal motion, a viscous flow, either laminar or turbulent, and irreversible.